Now I want to switch gears a little bit, and we're going to talk about hypothesis testing for proportions. And again, just like before, I want to do a little introduction first so you kind of know what we're dealing with. We're going to talk about all the different parts of it, and then we'll put it all together at the end. So this is an introduction of what a hypothesis test is. We just got done talking about confidence intervals, and we said, if we find this sample, we're whatever percent confident that the actual value falls within this range or this interval. So now what we're going to do is we're going to actually test it based on something that we are assuming is the actual correct P. So we're going to hypothesize what we think the population proportion is, which is of course P. And then we're going to test whether our data supports or does not support this hypothesis. So we're going to test for P and then say, yeah, our test supports that, or no, our test does not support that it could be that value. So again, think about a jury trial. To prove someone is guilty, we start by assuming that they are innocent. We retain that hypothesis, we say you're innocent until we have enough facts to say that beyond a reasonable doubt that you are in fact guilty. And then we can say, yes, we were going to reject the hypothesis that you were in fact innocent. Yes, you're guilty. Now the same thing, we never say, oh, you have been found innocent. We say you've been found not guilty. Not guilty means that's what we found. We didn't say you were innocent. We just said we don't have enough information to prove that you are guilty. So that's kind of the same process that we're going to look at with hypothesis testing. So in statistics, we can use the model proposed by our hypothesis. We're going to calculate the probability that the event we've witnessed or one more extreme could happen. Okay? And that probability is called a p-value. So that's different than the p hat, which is our sample statistic, and it's different than the p, which is our population proportion. A p-value refers to the probability that if what we're testing for is true, the probability that we would find what we did in our sample. Hopefully this will make more sense when we actually do a test. But again, we can't claim to have proved it, so we said we fail to reject the null, or if our p-value is very low, we're going to reject the null. Here's just sort of a big overview, and of course a lot of this you're not going to quite understand yet, but this will give you an idea of what we're moving towards. So we'll talk about conditions and all of those things in a little bit, but let's say here's our question. The cracking rate of casts in a steel mill is believed to be 20%. Okay, so believed to be, meaning that's not our p-hat. This is what we're saying, is this p, question mark. Is this the actual population proportion? That's what we're testing. Recently, a test of 400 casts produced 17% cracked. So that's actual statistics that we found. That's p-hat. Is this due to the new engineering process or random chance? So basically they're saying, hey, let's check whether or not it's actually 20%. So our null hypothesis, and we'll go into more detail on both of these in a little bit, but our null hypothesis is to assume that the proportion hasn't changed, that it's still 20%. So P equals 0.2. That's what I'm assuming, is that it's going to stay at 20%. But now they have this new engineering process, and they're saying, basically, is that lower now? Is the crack rate lower because we have a new engineering process? Did the change that they make a big deal? Does this 17% happen by chance, or did it happen because we changed some things? So my alternative hypothesis, I'm saying I'm going to assume that it's still 20%, but let's test whether it's actually lower based on the wording in this question. Now we're going to find a z-score. We all know how to do that, right? Here's my observed, my p-hat, minus my expected. I'm expecting it not to change. I'm dividing it by the standard deviation. So in this case, I'm not using standard error. I'm using standard deviation, which is 0.8 over 400. And again, I'm using that because I have a p. So that's different than when we had just confidence intervals where I didn't have a p, so I had to use p-hat and use the standard error. So I find negative 1.5, which we all know on our normal model, that's 1.5 standard deviations below the mean. And we all know how to find our p-value, which is essentially this. So the probability that our p is less than 0.2, sorry, that should be p hat, is less than 0.2 is equal to the probability that z is less than negative 1.5. And then I used my normal CDF or StatCrunch to find this, and I found 0.067. That means that 6.7% is the probability that if it were actually 20%, that I would randomly find 17% that were correct in a sample of 400 casts. So what does that mean? What kind of conclusion can I draw? Can I say, yes, it's definitely lower because my answer was 6.7%, or no, that's too close? Well, we don't know yet because we haven't really talked about it. If we're looking at a p-value of 1%, so 6.7 is sort of a, I don't know yet, we'll talk more about it later. If the p-value is 1%, that means it's extremely likely that this didn't happen by chance, because there was only 1% chance of it happening by chance based on the value that I gave you. If the p-value was 90%, so if I got 90 instead of 6.7, I would say, well, obviously that happens all of the time by random chance, and so it's okay, it's probably still 20. So how much is too much? Well, that's what we need to figure out with our p-values. So stay tuned for the next video.